this pre-calculus algebra video, we will continue our study of polynomial functions and their graphs. In the part 1, we looked at zeros and multiplicity. We looked at the intermediate value theorem, and we looked at the definition of what a polynomial function is. What we're going to pick up with now is we're going to look at turning points in a polynomial and its graph. And then we'll look at graphing a polynomial. Then that's where it all comes together. If you've not seen part 1 yet, I'd encourage you to stop this video and go back and look at part 1 video first. Take some really good notes. Make sure you understand what's going on in that first set of ideas, and then come on to this number 7 where we're picking up. Here's what we have. We've got this idea about turning points. It means how often does a polynomial turn and go the other direction? When we first started the section, we were talking about gas prices. So we might have had a gas price, and if it were gas prices, we wouldn't have an arrow. We'd have a point because it didn't keep going down infinitely, right? But gas prices, let's say in this year, started at one point, and maybe it dropped, and then it came back up. Now, this is a hot topic to talk about right now because gas prices have gone so high compared to what we're used to for right now. But even when it wasn't a time when there was a significant change, there's always a change, right? From one day to the next, we can see that it's turning and going up, turning and coming back down, turning, etc. So what we see here, if we went back and counted the number of turning points, we were rising and then falling. There's one turning point. Falling and rising, there's another turning point. Oh, and I forgot this one, falling and rising. That's the third. Rising, falling, there's the fourth turning point. And here's our last turning point, falling and rising. So we've got 1, 2, 3, 4, 5 turning points, or 5 times when we were going one direction and then went the other. So here in the graph that's sketched for you from our textbook, we've got 1, 2, 3, 4 turning points. Now that number of turning points has something to do with the lead term, or more specifically with the degree. This polynomial is degree 5, which means that it has at most, not guaranteed to have this many, but at most 1, 2, 3, 4, 5 zeros. If there's at most 5 zeros, then that's going to then say that at most we're going to turn around 4 times. So it's always 1 less than the number of zeros. So let me try to put this all together for you. The degree of the polynomial, so in this case it's degree 5, will tell us that there are at most 5 zeros. Now, why do I say at most? We're not guaranteed that there's 5. For example, if we look at the x squared, when we look at x squared, the parabola, a quadratic, degree 2, I'm going to say there's at most 2 zeros. But do you see that this parabola has no zeros? This parabola has 1 zero. This parabola has 2 zeros. We're talking zeros means when does it cross this x-axis? The first one crosses the x-axis never. Here we have where it touches and bounces back, right? And we know why, because it had multiplicity 2. That 0 had a multiplicity of 2. It's like this function, f of x equals x minus 3 squared. So here's the positive 3. The 0 was 3, but it was an even multiplicity, so it hit the graph and bounced back up. So we only got 1 0. So that's why I say at most 5. Or at most 2 for square, in this case, x to the 5th the most we could have is 1, 2, 3, 4, 5. But we're not always guaranteed that there'd be 5, but we are guaranteed there's not 6 or 7 or more than 5. With that multiplicity, we could see something bouncing and coming back. So we don't know that there are 5 zeros, but we do know that there's no more than 5. And then what we can say is that the number of times that we turn around is going to be 1 less than that. So if the greatest number of possible zeros was 5, then the greatest number of turning points is going to be 4, 1 less than that. So 5 minus 1. When we have a polynomial that's degree 4, so its highest exponent for the x looks like this, we know that there are at most 4 zeros, but the number of times it turns around, so the turning points would be at most 1 less than that, or 3. So that's turning points. Look at a few more examples of turning points and make sure you're really comfortable with that idea of the turning points. Sketch out a few examples to show yourself the number of turning points. All right, let's draw everything together from this section and use the 5-step strategy to graph this polynomial f of x equals x to the 4th minus 9x squared. To start with, number 1, we'll use the lead coefficient test to determine the end behavior. So the lead term is 1x to the 4th. The lead term is 1x to the 4th. That is an even degree with a positive coefficient. So I know that this behaves like a parabola, a positive parabola, a parabola opening upward. So we see that it rises to the left and it rises to the right. I don't know a lot about the graph yet, but I know that at most it crosses this axis 4 times, and I know that to the left it's rising and to the right it's rising. So I know that the end behavior looks like a positive or upward opening parabola. So that's the first thing I've got. Number 2, find the x-intercepts by setting f of x equal to 0. So that was number 1. Number 2, the x-intercepts. If I let f of x equals 0, so I have 0 equals x to the 4th minus 9x squared, I can solve that for x by factoring. I'm going to factor the GCF x squared. X to the 4th divided by x squared is x squared. Negative 9x squared divided by x squared is negative 9. And then I see that I've got the difference of 2 squares. So this x squared minus 9 factors to x minus 3, x plus 3. So I can see the 3 zeros are 0, 3, and negative 3. Do you see which of those 3 zeros bounces back? So it doesn't cross over the x-axis, but it has a multiplicity of 2, an even multiplicity. So that means that it bounces back. Here it is. It's that repeated root, the x squared. Because you see, I could have written that x squared. Oops, let me go backwards. I could have written that x squared as an x times x. Right? X squared is x times x. So I'd see that this 0 would have been repeated. So what that tells me is that we've got multiplicity 2, so this 0 twice. And that means that when I get to that 0, when I graph the 0, we're going to hit it and bounce back. It might be hitting and bouncing back like this, or it could be hitting and bouncing back like this, but it's not going to cross over at 0. So that's what we can tell from the x-intercepts, the 3 x-intercepts. I'm going to go ahead and graph those 3 x-intercepts, and they're x equals 0, x equals 3, x equals -3. So I'm making some progress towards looking at this graph. The next one, the y-intercept, that's really the easy one. If I have f of x equals x to the 4th minus 9x squared, then I can go back in to the x and replace it with 0. Replace the x with 0 to find f of 0 is 0 to the 4th minus 9 times 0 to get that the y-intercept is 0. And we already had that point here because we found that that was also the x-intercept. So we know, though, that it doesn't cross this x or the y-axis any other place. So that was the y-intercept. And now let's look at symmetry. Do you remember symmetry? How to determine symmetry? So to determine symmetry, we want to know if it's even or odd. And the way we do that is we find f of the opposite of x. So if f of x equals x to the 4th minus 9x squared, then f of the opposite of x, you see what's going to happen here? This opposite of x to the 4th, that's just x to the 4th because 4 negatives turn to a positive. And then we have minus 9. The opposite of x times the opposite of x is again just x squared. So I get the function back. F of the opposite of x is equal to f of x. So this is even, meaning there's symmetry here on this axis. The y-axis, everything to the right is going to be the same as what's to the left. We've got y-axis symmetry because the function's even. Now number 5, let's use the fact that the minimum or maximum number of turning points is n minus 1, where n is the degree of the polynomial function. So since this is degree 4, I know that we turn around at the very most 3 times. So I know now enough to be able to graph the function. Let me get rid of these pieces here. So if I know I'm starting up here, I've got to get down here, and I know that that -3 had multiplicity 1, so I know I cross through. And I know that at the 0, I'm going to touch it and bounce back, and then cross through when x is 3, and I know the end behavior has us going rising to the left, rising to the right. So it looks a little bit like a W, and that's it. That's going to be sufficient for the graph. We won't need to get more specific than that. Though eventually you could get to where you find how low these points go and maybe a few other points to get more precise picture of what these pieces look like. But for now, it would be sufficient to have what we see here with the purple sketch. Well, that wraps up the section. I hope that you found this to be helpful. If you do have questions about continuing your pathway towards understanding polynomial functions and their graphs, please don't hesitate to reach out to me, visit me during my office hours, or send me an email. and I look forward to helping you come to an even better understanding. Thanks for the work you're doing.